Okay, Assalamualaikum warahmatullahi wabarakatuh. I just want to make some additional video on the switch mode inverter. So we have looked into this. What is an inverter? Inverter basically convert the input DC supply to the load which require an AC type of voltage or supply. Okay, so you want to change from DC to AC. For example, you have a solar panel, isn't it? We have a solar system. So the solar panel will give you actually the output of the panel will be the DC form, and then you want to step up that DC, and then finally, if you want to put it back into your house, then you need to convert into AC waveform, isn't it? And therefore, we need to have a switch mode inverter. So for the first type of the single phase inverter, we have a square wave output, whereby the output is in terms of a square wave. So it's square wave is again an AC waveform. We have looked at the derivation of the harmonic contents of a square waveform. I hope you well you understand. You already understand how to get that Fourier series from this square waveform, whereby you will identify what is the symmetry of the waveform, and from that symmetry waveform it will assist you in getting the Fourier series, right? So we know that the IDC, the Fourier series waveform, the square waveform, always odd and half wave. It is an odd and half wave symmetry, and therefore it also, because of that odd and half wave symmetry, then the waveform is also automatically it is an odd and quarter wave. So based on that symmetry, then we can look into the table here, right? From this table we will look at the features or the condition, and also what happens to the AN if the waveform is the condition or the symmetry of the waveform of any kind of that symmetry. So if you have odd and quarter wave, the waveform, you don't have to find AN, because AN is already 0 for all N, which means if N is even or N is odd, which is the harmonic contents for 1, 3, 5, 7, which is the odd with components, and as well as the even components, which is 2, 4, 6, all of them for AN is always 0. And if you try to get the integration of that AN, you will get at the end the result is 0. Okay, so you know that for odd and quarter wave the AN is 0, but for BN, for odd and quarter wave, the BN has two conditions. One is it will be 0 for even N harmonics, whereby if you talk about, if you want to find BN, B2, if you are required to find B2, B6, B4, B12, they all are 0 automatically, because based on this property, because of the property said that Bn for N equals to even will be 0, right? So what left is for Bn with odd numbers. So this is the condition. If you have odd numbers, then the Bn can be found by having this equation, 2 over T over 4. So you just integrate up to the quarter of the wave. Remember, we have a square waveform, Okay, so you have this is 180 degree, and this is 360 degree, and this is 90 degree, and you have 270 degrees there, right? Therefore, you don't you it is enough for you, it's sufficient for you to integrate from 0 up to the 90 degree, which is t over 4. This is the property of odd and quarter wave, right? And this is IDC. Okay, so if you do that and then you replace the t with 2 pi, if you replace 2t with 2 pi, then finally you can evaluate for b and odd. Finally, you have this equation 4 over pi, 0 to pi over 2, which is 90 degree here. Make sure it is 4 pi over 2. You cannot put this as a 90 degree, isn't it? So because you are doing it in terms of radians, so it has to be pi over 2. And then the equation, the waveform, you have to look at the waveforms. What is the instantaneous equation for that? And you have to multiply by sine n theta d theta. Solve for that, then you will get b1, b3, b5, and the rest. Okay, but yes, and the rest. Okay, so if you look at this Fourier series waveform here, what does, you can repeat that, go back and do some revision and look at this AN, BN, whatever they explain in this note, and how to get that. Finally, you get this equation, which is Bn equals to 4 IDZ over n pi, 1 minus cos n pi over 2. And then you have this for Bn equals to 4 IDC over n pi, and n is always odd because n even, Bn is 0. Remember from the properties? So what left is only for the n odd, which is 1357. And finally, our target is actually to get the Cn. Okay, because the Fourier series is always described by the Cn. So you have An squared plus Bn squared. We know that An is 0. So Bn equals to 4 IDC over n pi, and n equals to 1357. Okay, and therefore you have this phi n, the angle could be tangent An over Bn, which is also equals to 0 because An is 0. And the Fourier series representation of that square waveform, this is current waveform, and that's why you have this IACT. Okay, so you have 4 IDC over pi, because n equals to 1 here, sine omega t, plus 4 IDC over 3 pi, sine 3 omega t, because this is third harmonics, this is fifth harmonics, and this is seventh harmonics. And if you want to draw that waveform, then you get this, we call it a harmonic spectrum for a square waveform. So I always stress on this, emphasis or stress on this, because it's very important, because that describes the output voltage waveform. And from that output voltage waveform, okay, we get the Fourier series, and now it is a voltage waveform. Therefore, it is represented by a voltage harmonics. This is all voltage harmonics. And if you look closely, the V load, the output load voltage, the amplitude here depends on the topology. If it's a half bridge, then the amplitude of that output voltage will be half of the input voltage. Okay, so if it's a half bridge, then there will be half of the input voltage. So in this example, the input voltage is 100 volt. Okay, this is 100 volts, so therefore the amplitude is 50 volts here. So if 50 minus 50, right? So if you solve using that previous note on the square waveform, then you'll be able to get all these components here, and also you can calculate the amplitude here, whereby I just show you. So for that first component, it will be for B1, a C1, which is for IDC Z. Before this we have IDC, but now we have the 50 volt Z. 50 volt for I over 1 pi. Right? So if you calculate that, that will be 4 multiplied by 50 is 200 divided by pi. Okay, and then that gives you C1. And next you have C2, C3, which is 4 multiplied by 50 over 3 pi, 200 over 3 pi, and the rest. You can find that, you can find that, you can find that, you can find that as well. Okay, so the question can trick, the question, the final exam, the test, could ask you on the what will be the C1, what will be the C3, what will be the C12, what is the C14, what is C7. So you must evaluate the integral. Yes, now you must show that the waveform is square waveform and it's an odd and quarter wave. You have to repeat that. You have to justify before you come to the conclusion that AN is 0 and BN is 0 for even and Z, and BN equals to 2 over T over 4, 0 T over 4, and you have F T sine N T dt and omega T dt. Okay, so you have to justify that, and then you must show that you finally you come up with the C12 equals to 0. Why? Because it is this condition, isn't it? The property of odd and quarter wave, which is Bn, or because with Bn is 0, then Cn is 0. C12 is 0, isn't it? Come again. B12 is 0, then C12 is 0. Right? You need to show that. Okay, and next is we have this quasi square waveform. Remember, so for quasi square waveform, look back at when we have this during rectifier, you have the waveform of quasi square waveform, isn't it? Quasi square waveform. If I'm not mistaken, it is the waveform of the full wave rectifier. Full wave rectifier. Full wave, three-phase full wave rectifier. Three-phase full wave rectifier. So go back and look at this three-phase full wave rectifier, whereby if you have that, then this is your final equation, the waveform, isn't it? So identify that there is a 30 degree here, and you have this is 90 degree, and then you have this 150 degree, isn't it? And that will be 180 degree. Okay, so that tells you that this is a quarter. Again, if you look properly, if you look at the symmetry, this is also we call this as a odd and quarter wave, isn't it? It is odd and quarter wave. Okay, so therefore you can find A1 is 0, isn't it? Because it's odd and quarter wave. AN is 0 for all F, for all N. Then you can find Bn equals to 0 for even N. Again, Bn equals to, I always remember the general equation, T over 4. Why T over 4? Because it's odd and quarter wave. Then you have f of t sine n omega t dt. Okay, and then that is the so look at that for a quasi square waveform, right? We don't have we call it a triplet harmonics, isn't it? Triplet harmonics equals to 0, which is 3, 9, whereas 15, all of this waveform equals to 0. Okay, we have proven that before. So look at that, go back to the notes and look at the quasi derivation of the harmonic Fourier series for the quasi square waveform, and we found out that it is when it comes to the triplet harmonics, it will become 0. But the best or the general equation that you need to actually understand is by using the table of properties of symmetry waveform. Okay, so if it's an odd and quarter wave, so what will be the properties? An equals to 0, Bn equals to 0 for all n, and then Bn equals to 2 over t over 4, 0 to t over 4, f of t sine n omega t dt. Just remember this, then you just evaluate that. I think your calculator can easily evaluate for B1, whatever B3, whatever B9 that you want, isn't it? Just from the calculator, if you put in the numbers, then you can evaluate that automatically. You don't have to solve you don't have to do the integration at all, because the calculator can evaluate if you have whatever if you have all these parameter, then you can easily calculate for that B1, B3, B5, B9, isn't it? Okay, so that is a square waveform. Then we have this I'm going to come back to this PWM switching scheme, because this is also important, the pulse width modulation. Yes, so you need to understand what is a unipolar PWM and what is a bipolar PWM. Okay, all right, unipolar and bipolar. I will come back to this, but I'm going to proceed with the three-phase inverter. Okay, so for three-phase inverter, there are three types of sorry for this, right? So there are three types of a three-phase inverter. You can have a 120-degree conduction mode, you can have a 180-degree conduction mode, and finally you can also have the same sinusoidal PWM waveform. Okay, so you need to differentiate, and you need to understand how to produce the 130-degree conduction mode inverter, and as well as the 180-degree conduction mode, as well as this sinusoidal PWM. So for 120-degree conduction mode, look at that. So this is still the same. We call it this is a full wave inverter, full bridge inverter. So you have S1. Remember, the labeling is always S1. It's always S1, 3, 5, and then you have 2, 4, 6. It's always in that arrangement because that will make sure that your inverter works properly. Right? So you have S1, S2, S3, S4, S5, S6. Okay, this is not randomly labeled. This is actually to make sure that the switches act accordingly based on the arrangement. So it always have to be S1, S3, S5, S2, S4, 6. And then it is connected to the load, and you give a 120-degree pulse to each switch, remember? And now you have a sequence. You have to follow the sequence of arrangement. Okay, so you have S1 here, S2, S3, S4, S5, and S6. So if you do not arrange according to the labeling just now, you mix up, you have this S1, S2 pulse, but you mistakenly label, or you have this S1 and then you want to have this S2, S3, S4, S5, S6, then your inverter will not function as what you want. You won't get that 120 connection mode inverter. Okay, so it is labeled in this such a way so that you have a proper output voltage. Okay, so you have S1, S2, and then you have 120 degree, and then there is a phase shift of 60 degree from switch 1 from switch 1 to switch 2, and then you have further 60 degree from switch 3 and switch 2, and you have another S4 to S3, you have S5, S6, and finally S6 and S5. Okay, so because of that, you look at, first you must look at the phase voltage, right? The voltage across the phase resistor. You only focus on two phases, phase 1 and phase 2. So that gives you this gives the phase voltage across the resistor 1, phase voltage across resistor 2, and this is the line to line voltage between phase 1 and phase 2. Okay, so you have three different voltage waveform here. This is phase 1, phase 2, and this is the line to line voltage between phase 1 and phase 2. So if you are required to find the if you are required to find okay, so if you are required to find the Fourier series of the waveform, you have to observe the waveform, this waveform first, right? So if you look closely, is there any symmetry that the waveform has in this position? So this is 0. If you look closely, this is 0. Then you have this 120 degree, sorry, 120 degree. This is 180 degree, and then you have this 120, so this is 300 degree, and this is 360 degree. So if you look at this waveform, actually you won't get the symmetry that this waveform has is only, what is that? You have to, if it's odd, so how to identify the waveform is odd? So you have to what do you call it? You have to fold, reflect. Okay, so you have to reflect with respect to let's say this is your axis, y axis, and this is your x axis, isn't it? Okay, let me redraw that again. Let's say that we shift this 0 to here. Okay, so you have 0 over here. Let's see, this is your y-axis, and then this is your x-axis. Okay, right. So what is this waveform is odd? So if you want to identify the odd, you have to reflect respect to y-axis. So you will get that waveform here. Sorry, you have that, then you have that form 0. Okay, and then you reflect respect to x-axis, and then you reflect. So therefore, if you maintain that waveform, it is not odd, isn't it? It is not odd waveform. What about even? So if the waveform is even, it is enough for you to reflect respect to y-axis, and you get the same waveform, the original waveform. So obviously, if you reflect respect to y-axis, you won't get that original waveform. So therefore, this is also not an even waveform. What about the half wave waveform? So how to identify whether this waveform is half wave? You have to shift to the left half with half cycles. So let's see, this is half of the waveform. Okay, I'm going to redraw that again. So this is our axis. This is the axis. Okay, so this is the axis, and then this is the this is first half, and this is another half here. So you shift the waveform to the left half cycle, shift to the left half cycle, and therefore you will get, this is shift, so you get that, waveform, isn't it? Okay, you get that waveform, and then you reflect with respect to x-axis, and you will get the same waveform, original waveform. So this waveform, it is only half wave waveform if you maintain the original waveform here. But for the magnitude, if you want to find the magnitude, which is A1, AN, BN, you can also actually move the, or you can modify the waveform such that you can actually, move the zero axis anywhere. So if I put this as a zero axis, y axis there, then you have x axis there. Okay, look at that. What happens? So you have 0, and this become your pi, and this is your 2 pi, isn't it? Okay, so if I modify a bit, so I will get this 0, pi, and 2 pi. So if you focus on that waveform, this is actually what? A quasi-square waveform, isn't it? This is a quasi-square waveform. So if the purpose is only to get the coefficient A and Bn, then you can use this methods, which is you shift or you move, you modify the y-axis here anywhere, right? So in this case, if you put this in that 30 degree here, so that you have a from there to there is 30 degree, then you have 120 degree again here to there. Okay, so you will get this equal to a quasi square waveform. So we have looked into the quasi square waveform just now, whereby it is odd and quarter wave. It is an odd and quarter wave waveform. So therefore, AN is 0, BN is I call it 0 for, and this is for all N, and this is for even N, and you can find Bn equals to 2 over T over 4, 0 to T over 4, and f of t, f of theta, f of t, sine n omega t dt, isn't it? So you evaluate that, then you get the. So remember, this is amplitude actually depends on whether it's a half bridge or full bridge. Okay, so if it's a full bridge, then this is input voltage, whatever VD input. But if it's a half bridge, then V in over 2 the amplitude here. Is it? Okay, so just to remind you. All right. Okay, so then you can there. So what happens to this? In V line to line. For example, you want to find the harmonic contents of the line to line voltage here. So if you look carefully, so as I mentioned just now, your waveform starts from there, isn't it? Start from there. So if you do the identify to whether to identify odd and quarter wave, you won't get that. It is not odd and quarter wave, but if you look carefully, it is the half wave only. It's a half wave waveform. So you perform the same adjustment. So if I can bring that axis to there, for example, if I move this to here, okay, this is 0, and then this is pi, sorry, this is pi or 180 degree, and that will be my 2 pi or 360 degree. So if I move this to that waveform, that axis, this waveform is what? Look at that. Look again. This is odd and quarter wave as well. It is odd and quarter wave as well. Okay, so you have this as a look at that. This is 50 volt, which is V in, and that is 100 volt. Okay, so this is 100 volt there. Okay, so this is 100 volt here. So here you have 100 V in over 2, and that one is V in. Okay, right? So again, look at that. So this is odd and quarter wave. Therefore, you only integrate up to that waveform, that 90 degree, or pi over 2 pi pi over 2, isn't it? Yeah, you have pi over 2 there. Pi over 2, pi to pi. Pi over 2 is 90 degree. Wait. I think I've made a mistake here. Yes, still it is correct. So you have this. What is it? Where is it just now? Quarter of the wave, isn't it? So this is t over 2. This is t, and that will be t over 4 here, isn't it? So t over 4, which is 90 degree, right? So you need to evaluate only from 0 to 90 degree. Okay, and therefore you have two integral that you need to solve. One is when it's a 50 volt, which is equals to V in. Okay, and that's from 0 to, what is this? 0, this is 30 degree, that is 60 degree, and this is 90 degree. So you have to evaluate from 0 to pi over what? Pi over 6. No. Pi over 3. So from 0 to pi over 3, and then you have to evaluate from pi over 3 to pi over 4. Wait, this is pi, this is 2 pi, pi over 2, isn't it? So here you have pi over 2. So you have to evaluate from pi over 3 to pi over 2 for this value. So 50, and we have 100 volts. Okay. So your still this is odd and quarter wave. So therefore a n equals to 0. All n. Pn equals to 0 for even n, but Pn equals to 2 over t over 4, 0 to t over 4, and you have v now, vt sine n omega t dt, and if I go further, we'll get 8 over t 0 to t over 4 vt sine n omega t dt, and if I replace that t with 2 pi, then we get 8 over 2 pi, and that becomes 0 to 2 pi, so you have pi over 2 here, v over 2, v over v theta sine n theta d theta there. Okay, and finally my bn equals to 4 over pi, and I'll only evaluate from 0 to pi over 2 v theta sine n theta d theta. Sorry for that. Okay, so here if I want to find b1, so I will replace all that. B1 equals to 4 over pi, and becomes 0 to pi over 2, and that become, again, I'm going to write that again, b v theta sine, and now it's 1, did it? So sine theta d theta. Okay, then if I go back to the v line to line voltage here, line to line voltage, I will have two components here. 4 over pi. I must have two components whereby I will integrate from 0 to 60 degrees, isn't it? 0 to pi over 3, and the amplitude is 50 volt, and you have sine theta d theta plus, I'm going to have from pi over 3 to pi over 2. I'm going to stop that, and this is 100 volt sine theta d theta. Is it? Okay, so from there I can find what is P1. I think you can solve that using your calculator. Okay, straight away you can do that. Then you get what is a P1, and finally you have C1 equals to, of course, we know that A1 is squared, A1 is 0, A1 squared plus B1 squared, therefore it is B1 squared. It's always a magnitude of B1. So you calculate what is C1. Then look for B3, for example, if you like, because we know that B2 is 0, isn't it? B2 is always 0. And now look at B3. So B3 can now become 4 over pi, and then this becomes 0 to pi over 2 again, V theta. Now you have sine 3 theta d theta z. So say you have to have two components, which is that component and that component. But now you have this become, you have to replace with 3 theta there. Okay, so we have 3 theta, and then solve for this. Then you get what is B3, and therefore you can identify what is C3 as well. Okay, right? So that is for 120 degree inverter. What about, look at that, they all have, if you can, if you observe, those phase 1 and phase line to line voltage and phase voltage, they have the same property, which is there is no triplet harmonics. This is triplet harmonics. So there is n equals to 3 is 0. This is 9, n to 9 also 0. This is n 15 also equals to 0. But you have to prove. You have to prove first, because the waveform is not a quasi, a simple quasi. Now you have the line to line voltage is in the form of this waveform, sorry, slightly a modified version of the quasi square waveform, sorry. It's not simply like that compared to the square waveform we have for phase voltage. So this is your phase voltage, and this is your line to line voltage, right? Okay, so what about the 180 degree conduction mode? So again, we have the same arrangement, 1 3 5 2 4 6, and then the switch signal to the switch is different. You have 0 to 180 degree instead of 120 degree. Now you have 0 to 180 degree. Just again, we have 60 degree phase shift between each switches there, and that the signals that supplied, that provided to all switches there. And finally you found out that the phase 1 now has the shape of the line to line voltage for 120 degree inverter just now, isn't it? So it is opposite waveform. So for phase 1 you will get this waveform. However, for the line to line voltage we have this square waveform, right? But you have to be careful with the amplitude now. Okay, so just do if you follow this, now you can straight away, you don't have to modify the axis because you can do that axis. You can maintain that 0, and then you can maintain that. Of course, this is x-axis always, isn't it? So this is y-axis, and this is x-axis. Okay, so now you have to identify what is this amplitude. I think from the note, go back to the video, the previous video. What will be the amplitude for this? It's no longer like the 120 degree induction, 120 degree conduction inverter. In 120 degree conduction mode, the amplitude is always V in over 2 here, and you have V in over and the top one will be the V in for line to line, isn't it? But this is different. For 180 degree, you go back to the previous note, previous video, identify what will be the amplitude for this. I can't remember. And go back, and what is the amplitude for that, right? And the rest is similar to the derivation just now. So you need to, if you look at that, this is odd and quarter wave. Therefore, an equals to 0 for all n, and bn is 0 for even harmonic, even n. Bn only exists for 2 over t over 4, 0 to t over 4, v t sine n omega t dt. Then you can change that 2 to 2 pi, then you give to 4 over pi, 0 to pi over 2, then you have v theta sine n theta d theta, right? Then just similar, just what we did just now. So you may be asked, what is a B1, B3, or B2? For example, B4, they just want to ask you B5, B12, B9, whatever it is. You can you have to find B1, B3, and then remember our objective is actually to get C, C components. But of course, you have to derive for coefficient B1, B3, B4, B5, B9, and the rest. So you get that. See why? Because in harmonic contents, if you look at the harmonic contents, it is always represented by the harmonic contents, isn't it? We have C1, for example, C3, C5, and the rest. Okay, so it is not B1, B3, but it's C1, C3, C5. Okay, right? So that is on the first part, the inverter. Now I'm going to come back to the PWM. Right, PWM, pulse width modulation. Okay, for the SPWM switching scheme with full bridge topology. So for the SPWM, which is the sinusoidal pulse width modulation. So why it is a sinusoidal pulse width modulation? Because the modulating signal, remember, the modulating signal is sinusoidal signal. Remember, we have modulating signal and carrier signal, isn't it? Okay, since the modulating signal is of the type of sinusoidal signal, therefore it is known as an SPWM switching scheme. The carrier signals can be a triangular waveform. Okay, and for this EPO 510, we only consider the normal triangular waveform, because in reality, in practical, you can have a sawtooth type of waveform, which is not symmetrical. It can be that sort of waveform. Okay, straight, then have a slope. So it is known as a sawtooth waveform. Okay, so but for the EPO 510, we only consider this a normal triangular signal waveform, right? So, and therefore, there are two types of SPWM switching scheme. One is the unipolar PWM, and the other one is bipolar PWM waveform. So, how to identify whether it's a unipolar PWM or bipolar PWM? This is simple as this. Remember, to produce the PWM signals, we need to have modulating signals compared with the carrier signal, isn't it? So you need to compare both signals, and you look at the condition of if the modulating signals is higher than the carrier signals, the output will be 1. If the modulating signals is lower than the carrier signals, the output is 0. Okay, so for unipolar PWM, what differentiates between unipolar and bipolar PWM is that for unipolar, the carrier signals only consist of the signals, the carrier signals, the triangular carrier signals, which is only have a positive value. It is a triangular carrier signals, but it's always positive only values. Okay, so let's say this is a VCM, VC, the amplitude of the carrier signals, and then you compare with the sinusoidal modulating signals. Okay, I will show that. So for bipolar, what differentiates is that for bipolar, so this is unipolar. So for bipolar, the triangular carrier signals consist of positive and negative values. Normal carrier signals here. So this is the bipolar PWM. Right? So you have VC amplitude, and that one will be minus VC amplitude there. However, for unipolar, you have only 0 to VC. Isn't it? Yeah? So this is bipolar PWM. And then compare with the sinusoidal signal. So let's look at this example. Right, look at this example. Okay, look at that. So for this, we just focus on this one of the PWM signals. Look at that. So the blue waveform is here is the triangular carrier signals, and then we have the compared with the sinusoidal signal. Okay, it is compared with the sinusoidal signals, and the red waveform there is the output, and this is actually the switching signal that pass to the switches. Okay, so to create that SPWM signal, you need to compare between modulating signal, sinusoidal modulating signals, with the unipolar, which is the positive only triangular carrier signals. Okay, so you compare that, then whenever you see the if I can zoom that further, okay, zoom that. Okay, so whenever you see that the modulating signal is greater than, you see that the F, if I can show that, if Vm is greater than Vc, therefore the SPWM V SPWM equals to 1. Okay, for example, in this area here, so from that point to that point, you see that the modulating signals is greater than the carrier signals here, isn't it? And therefore it will create the one output signals of 1. So whenever the voltage is 0, whenever look at that, from there to there, let's see from okay, let's look at this question here. So here you see that the Vm, this is your Vm here, is lower than the carrier signals, and therefore the PWM equals to 0. So it creates a terrain of pulse, and here for the negative half cycles, always a 0, isn't it? Why? Because you see that the modulating signals is always lower than the carrier signals. That's why at the negative half cycles, the PWM signals is always 0. Okay, and this is with, if I can trace, this is, look, but the amplitude is 0.8. Okay, and we know that the modulation index is always Vm, the modulating signals, the peak of the modulating signals, divided by V peak of the carrier signals. So the carrier signal is always 1, and normally it is fixed. Okay, so you fix the carrier signals amplitude, you vary the modulating signal. So here you're going to vary this modulating signals peak to get a different value of modulation index, but you fix that Vc, and you're going to fix that carrier amplitude, but you vary the modulating signals amplitude. Okay, so what happened if you, and again we also have this frequency ratio, isn't it? Frequency ratio, which is the frequency of the carrier divided by the frequency of Fm. So if you have this is example 3. So if you have, this is Fm, and you have this and if you have this as a carrier signals, Fc, so what will be the Fr? Frequency ratio equals to, okay, so you have, this is your Fm. You can actually count, right? So in one full cycles here, how many triangular repeat itself? So here we have 1, 2, 3, 4, 5, 6, 7, isn't it? So you have 7 frequency ratio. This is 7 frequency ratio, because your Fc 7 times higher than Fm. Sorry. So you have Fc, which is 7 times higher than Fm. So therefore, Fr equals to Fc divided by Fm. This is important, right? As well as the modulation index. So M equals to Vm peak divided by Vc peak. Okay, from there, if you look carefully, this is 0.8 and this is 1. Okay, so what happened if you vary the amplitude? Let's say if I want to lower that to there. Okay, let's see. This is unipolar, isn't it? This is a unipolar. What if I have that sort of, let's say this is what, 0.3, for example. Okay, so if I do that, what happens to the pulse? It will be different, isn't it? Because now here I will see that the pulse here getting smaller because the intersection now getting smaller here, so I will get a smaller pulse there, and then that also getting small here. Can trace that. Okay, you can also draw that if you like. Okay, you can draw that as well. You can draw that as well. You can draw that, and look at that. So now this is getting smaller. So if you compare the final results, the pulse is getting smaller. The width of the pulses getting smaller as you lower down the moderation index. But if you increase the moderation index, let's say moderation index become to 1. So this is your moderating signals of 1. M equals to 1. So therefore, your pulse getting bigger, isn't it? Because now you have the cross there and there. So your pulse getting bigger compared to the previous, the original. So this is 0.8. So the pulse getting bigger as you increase the moderation index. Okay, so I hope you'll be able to look at this, and then you trace, you can draw. Okay, you understand what is the parameter given to you. Okay, what is the frequency ratio, what if you change the frequency ratio. Okay, so if you look at this examples here, the notes, if I can calculate or determine what will be the frequency ratio here, I can easily count. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Sorry, it's end up here. So you have 20. So your frequency ratio is 20. Your frequency ratio is 20. So therefore, your FC is 20 times 50 Hertz. So therefore, it is 1000 Hertz. The FC is 1000 Hertz. Okay, right. So if I go back to the previous page, therefore, yes, exactly. Your MA equals to 0.8 modulation index, and the frequency, the FC of FS is 1 kilohertz, because this also determine the switching frequency. Okay, so that determines the switching frequency. And for the unipolar, you need to have two different comparator. This comparator to fit as, if you refer to this, it will give to S1 and S4. But for this comparator, it fit the diagonals, which is there and that one, is it? Okay, so you must have two comparator because the moderating signal is different, right? For the unipolar PWM, so you have different. Look at that. The moderating signal is the mirror image of the mirrored version of the moderating signal for SPWM1. Okay, so you can apply the same as bipolar, and don't worry about the uh, forget about that. Okay, actually you can also find the moderating signals for this sorry, the coefficient, the Fourier series of the PWM here, but will not be covered, so don't worry about that. And you can identify the first component by using this equation. The fundamental, the amplitude of the fundamental is always MA multiplied by VE, because this is a this is a full bridge. Okay, it's a full bridge, so you multiply by V in. Right, and then for bipolar PWM it will be different. Okay, so for bipolar PWM, the carrier is again the same carrier signals, a triangular carrier signals, but it consists of positive and negative. So I hope you'll be able to draw that and trace the SPWM. You can draw the SPWM1. You can identify what happens if the MA increase, MA is reduced, what happens frequency ratio if it increase or reduce. Okay, so this should be understood. Just practice, right? Just practice and then compare with the simulation. That's the best you can do, right? So look, don't forget about the bipolar PWM. It is also important. Look at the PWM as well, the bipolar PWM, right? And I think that's all. That's actually what we covered for EPO 510, right? Okay, so any question, just drop me a line, just text me, PM me if you like. Inshallah, I will be able to answer. Okay, with that, Assalamualaikum warahmatullahi wabarakatuh.